Okay, welcome back. We're very happy to have as our next speaker, Theo Johnson-Freyd, who will talk about mock modularity and a secondary invariant.
So thank you very much for the introduction and for the chance to speak. I also, since I'm the last speaker, I get the pleasure to thank the organizers, to Jeff and Nathan and everybody on behalf of everybody. So if it's possible to unmute everybody to applaud for them, that would be really great.
I've just done that, and let's please applaud. Now I will mute everybody again, which means, Theo, you have to mute yourself. Unmute yourself, rather.
Great. So, right, so I'm going to talk about mock modularity and a secondary invariant. And most of what I'm going to say is based on joint work with Davide Gaiotto. I also want to say I despise slide talks. I hate them, I hate them, I hate them. I'm really excited for when we can all go back to giving jock talks to each other. The reason I despise slide talks is because I can't go back on my own and see what people said. So if you're like me, please download the slides. I put the link up and you can flip through them at your own pace. Okay, now I'm going to remove the link. So my plan for the talk, I'm going to say, I want to tell you about a new invariant that's a secondary invariant. Secondary meaning that it's comes from the Witten index, but it's a kind of secondary version of the Witten index. So the primary invariant would be the Witten index. And it's an invariant, a deformation invariant of supersymmetric field theories that we discovered. So I'll say just a little bit about what I mean by deformation invariant of supersymmetric field theories and about the space of supersymmetric field theories that I want to think about. And then I'll spend most of the talk kind of first reviewing what I think something that I think you are almost all of you are probably very familiar with, which is the Witten index itself, or the elliptic genus, or whatever you want to call it. And then I'll tell you our new invariant. And then at the very end of the talk, I'll just say some kind of obscure things about mathematics. So, so the context of the problem, there's a very general problem that I think a lot of people would be interested in knowing ways to solve. So, given any quantum field theory, but in particular any supersymmetric field theory, and in my talk, I'm only going to care about 1+1 dimensions, unitary field theories with minimal supersymmetry, but these are questions you could have asked in any dimension and for any amount of supersymmetry. The first question you could ask is maybe the simplest, which is just, is supersymmetry spontaneously broken in your theory? And if it's so, I'm going to call the theory null, because those theories kind of behave like zero in the far IR. At least they behave like zero if you really only care about the supersymmetric ground states. Another question that high energy physicists have often asked is, maybe you have a theory where supersymmetry is not spontaneously broken because of some fine tuning, but maybe you could trigger a spontaneous supersymmetry breaking by deforming the theory in a supersymmetric direction, by adding an operator to the action. The third question, which is the question I actually care about, is whether you could trigger spontaneous supersymmetry breaking by a large deformation to the theory. Maybe by some path in the space of field theories. Maybe there's a path, for instance, I want to imagine paths that are, for instance, allowed to flow backwards up against the RG flow, meaning that anything that is above you under RG flow is something you're allowed to flow to, you're allowed to flow back down, you're allowed to form, always preserving supersymmetry. Can you get to something with spontaneous supersymmetry breaking? If that's possible, I'm going to call your theory null homotopic, because it's homotopic to a null one. Now I want to flag that these questions, especially question 3 about null homotopy, this depends very sensitively. Whether a theory counts as null homotopic depends on how I've topologized the space of quantum field theories, and really on what analytic decisions I make about quantum field theories. I will focus on the case where I have quantum field theories. Oh, before I say this, let me just say that this question of kind of deforming, where you maybe flow down to an IR and then back up against the RG flow. I know that Zyberg calls that the condensed matter topology on the space of field theories. because I consider two theories kind of deformation equivalent if they have the same IR. So anyway, so what I was going to say is I need to be careful about analytic questions, and I can't be as a mathematician. We don't even have a definition of 2D quantum field theory at all. So I'm going to say kind of what I think the analytic questions should be roughly. So roughly speaking, I want to work with compact quantum field theories. My working definition of compact is that the Wick rotated partition function, the Euclidean partition function, should converge absolutely uniformly to an analytic function. And it would be really great if we could do enough analysis to get that really precise. And roughly the topology is called, it would be something like the strong convergence of the resolvent of the Hamiltonian. This is a topology in which eigenvalues can go off to infinity, in which case the corresponding eigenvector just disappears from the theory. And the reason I want this compactness condition is because I believe that if I ask these questions for non-compact theories, then the whole space of non-compact theories would be contractible. I believe that every theory would connect to zero under a deformation. So to make this really kind of hands-on, let me just work through an example, which is an example that's kind of a textbook example from, so I'm sure most of you are going to be able to do it maybe even faster than me. So I could start with free scalar multiplets. So let me remind you that means that I have a full boson and its right-moving superpartner. This is an example of a non-compact theory. I could add to this theory a left-moving fermion, or rather a Fermi multiplet, but its superpartner is auxiliary, so I'll leave it out. Still non-compact, but now I could deform the theory by turning on superpotential, and the potential that I want to choose is phi squared minus epsilon all times lambda, where epsilon is going to be a parameter that I'm going to vary. And with that deformation, this is now an example of a compact quantum field theory. So now we can study what happens at different values of epsilon. And when epsilon is negative, it's not too hard to show that this theory is null. Supersymmetry is spontaneously broken. When epsilon is positive, there are two massive vacua to this theory. And when epsilon is zero, the theory ends up flowing in the IR to a 1-1 minimal model. So this gives me a family of theories, an example of a family of theories. It's where if I run epsilon from plus infinity to minus infinity, you get a family that starts at a theory with two massive vacua, that in the IR is just a topological field theory with two completely independent universes. And it deforms that through a CFT back down to a null theory. And I want you to imagine that deformation as being a cobordism. If you graph this function phi squared minus epsilon, you get a cobordism from empty set to 2 points. If you graph the fibers of that function. So the reason I wanted you to think about it as a cobordism is because in general, cobordisms give a good way of producing null homotopies. They don't produce all null homotopies, I don't think, but they're a good way of producing null homotopies. Maybe they do produce all null homotopies, actually. Well, anyway, so I'll say this a little too quickly, but let me remind something that I think maybe goes all the way back to Greg Moore's thesis, which is that in order to give a minimal supersymmetry, in order to write down a sigma model with minimal supersymmetry, the target manifold has to have some structure that enhances a spin structure. In mathematics, the structure is called a string structure. It's a quantum B field with so that's the flux of a quantum B field. And it makes sense to talk about cobordisms, families of manifolds, where the topology is allowed to change, but just like the topology in this family of manifolds changed if you look at the fibers, where the total space of the cobordism also has a string structure. What we argued with Edward and Davide was that if you have a cobordism with string structure, you can turn it into a homotopy of sigma models on the fibers. And the way you do that is just an enhancement of the example I did, where I take the theory for the whole cobordism, turn on a left-moving fermion, which will act as a Lagrange multiplier, turn on a superpotential and that forces you onto the fibers of the cobordism. In particular, if I have a manifold which is string null cobordant, meaning it's the boundary of another string manifold, then the corresponding sigma model is definitely null homotopic. And the example that we wanted to think about was the case of the round S3. Now, it's a kind of not very hard computation to see that in kind of topology, to see that the possible choices of string structure for the round S3, that there's basically Z of those. And the far IR, you can try to convince yourself is going to be basically a supersymmetric WCW model, where S3 is behaving as the group manifold of SU2. That's why you get a WCW model. And the string structure, the strength of the string structure ends up becoming the WCW level. So I might use those words interchangeably. And what happens is that when you have the string structure being 24, or generally a multiple of 24, then this manifold is string null cobordant. Very explicitly, it's string null cobordant by a punctured K3 surface. And so that implies that the WZW model, the supersymmetric WZW model with a particular WZW level, with level divisible by 24, is null homotopic. And our question was, is this true for other values of K? Where you, in topology, you can prove that there's not a topological, like there's not a cobordism that would give you a null homotopy, but maybe there's a quantum null homotopy. So that was our motivating question. So now let me spend most of the talk telling you about the way we solved the question. So how would you show that a theory is not null homotopic? Well, the way you'd have to do it is you'd have to find a deformation invariant, meaning something that doesn't change as you move around the moduli space of field theories, which is not 0 for your object and 0 for the null object. And there's a very famous example of such a deformation invariant for these minimally supersymmetric 1+1D theories, which I think I will call the Witten index, although in topology it would be called the Witten genus, and maybe some people call it the elliptic genus. The definition I'm going to take is that, and this is up to some normalization conventions that you have to pick, but the definition is, or a definition is that this is the Wick rotated, so the Euclidean partition function of your theory on flat tori with non-bounding spin structure, meaning that the spin structure on the world sheet is Ramoned in every direction. So although this is a very familiar object, I want to review its basic facts because I'm going to extend those. So a priori, in my definition, this is a function on the moduli space of flat tori, maybe an analytic function if you can do the analysis correctly for quantum field theories. Well, the space of flat tori is 3 real dimensional. It has the it has the complex structure, which is 2 real dimensions. I'll polarize them to be tau and tau bar. And there's also the area of the torus. And maybe there's some analytic properties like that in the tau to I infinity limit, it should not blow up too badly. Like a pole constrained by the xenologic of Z function. So although a priori this is a function of 3 variables, in fact, very famously, it's a function of only 1 variable. It's a modular function, a holomorphic modular function. So let me remind why that's true. And I know you're going to all be bored, you're going to all zone out, but bear with me. So the reason why this is a function only of the variable tau and not of tau bar in the area is, well, there's various ways to see that, but the argument I want to use is from the path integral, where if you ask what's the derivative, say, in tau bar, in general, if you ask what's the derivative of the partition function under something where you change the geometry of the world sheet, the answer is always up to some proportionality factor, always the 1-point function of a stress energy tensor. That's the definition of stress energy tensor. So if I deform in the tau bar direction, I get the z bar component of the stress energy tensor. If I deform in the area, I get something proportional to the z bar component of the stress energy tensor. And the supersymmetry algebra tells me that these 2 components of the stress energy tensor are each superderivatives. I mean, they're each SUSY exact. And since I'm only in minimal supersymmetry, the ZZ component is not SUSY exact. But these 2 are. And then the point that I want to emphasize is that for a compact quantum field theory, the 1-point function, working in this non-bounding spin structure, the 1-point function of anything SUSY exact ends up being 0. So that proves, that's the reason why this Witten index is holomorphic modular form, or technically a weakly holomorphic modular form, because it can blow up with the pole at tau equals I infinity. So that's the first basic fact about the Witten index. The second basic fact is that it's not just a modular form, but it's actually an integral modular form. So the standard argument for this goes, or a standard argument goes, let's break the manifest modularity by choosing a small a cycle and a long b cycle. And then in that limit, you can recognize the Q expansion of this modular form as the supersymmetric index, as a count of SUSY ground states for a quantum mechanics model. And then you get integrality for the Q expansion. And the S1 equivariance just counts the order, the power of Q. Since integers cannot deform, this function, which was a priori just a function from the space of quantum field theories of SQFTs to the space of integral modular forms, well, it must be a locally constant function because the space of integral modular forms is discrete like the integers are. And so this must be a deformation invariant. And so if you have a theory with non-zero Witten index, it definitely cannot be null homotopic. Unfortunately, the theory I care about has trivial Witten index, so this doesn't solve my problem. But it was a good first guess. Okay, so I'll come back to my invariant, but I want to continue to explore this Witten index a little bit because it'll be what we thought through to come up with our invariant. So let's ask now, my argument used some compactness. It used we use well-definedness of these functions. So I can ask, what happens if if my field theory that I'm trying to evaluate the Witten index of is not compact? Well, if it's badly non-compact, remember my definition of compactness was that partition functions converge absolutely. So they're very well defined. If you have a badly non-compact quantum field theory, then there's just no reason for partition functions to converge at all. For the integrals to converge, or however you want to write them. So you just don't have a well-defined Witten index at all. This is part of why you might think, why in some examples the Witten index can jump in a family of non-compact theories, because it can just pass through somewhere where the Witten index isn't even defined at all. But another case that's interesting to consider is what I'll call kind of mild non-compactness, where an example of a mildly non-compact theory is the cigar model, the cigar sigma model. And in general, I want to think about theories where you have, and I should emphasize, not all of my theories are sigma models, but I'm going to use language as if they are. So I want to imagine theories where there's some interesting part of the field theory, and then there's a sort of cylindrical end that looks like some other theory that I'll call X just times the real numbers. The definition we use for this is that I could take a theory and maybe select some interesting observable, capital Phi. For any observable, it makes sense to talk about the fibers of that observable by by adding in a fermion to be a Lagrange multiplier, turning on a superpotential. And then it makes sense to ask if the theory, then maybe I'll say Y has cylindrical ends X if I can find some observable Phi such that the fibers of Phi are null for epsilon very negative and X for epsilon very positive. And I'll just write this as the boundary of theory at Y is theory X. I want to emphasize, you should think of this as a boundary in field space. This is not a boundary on the world sheet. So if you do have cylindrical ends, and if the partition function of the X theory is 0, then the contribution of the partition function from this long end looks like 0 times the volume of the real numbers, which we can set to 0. And we get a conditionally convergent partition function. So conditionally convergent Witten index. And if I define this just in terms of like a partition function for a torus, it's still manifestly modular. But it might depend again on the both complex and anti-complex structures of the world sheet. It might be real analytic rather than holomorphic. So let's probe, is it really real analytic? Let's run the argument again. So part of the argument just compiles. If I try to ask what's the derivative of the partition function with respect to the tau bar direction, that's still just the expectation value of inserting the z bar component of the stress energy tensor, and that's still proportional to something, the expectation value of something SUSY exact. But now the problem is whether the expectation values of SUSY exact functions do or don't vanish. Well, why did they vanish before? It's because SUSY exactness is sort of like being a total derivative. That's how you should think about it in the path integral. And so, so what you should expect is that if you have an end, if you have a boundary x, then instead of the expectation value of something SUSY exact being 0, you'd get a boundary term, like in a Stokes theorem type statement. So this was our argument. We didn't try in the paper to make this argument completely, like we didn't try to handle a lot of details that you might worry about in quantum field theory to make the argument really compile, although I think one could do that. And in a paper from the spring, Edward and a couple of collaborators who I'm forgetting worked in much more carefully in the sigma model case. But we just checked a bunch of examples to get the proportionality correct. And what we claim is that the tau bar derivative of the Witten index for these theories with cylindrical ends times the Dedekind function of tau times minus the square root of minus 8 of the imaginary part of tau, that's the expectation value of the z bar component of supersymmetry in the boundary. And this is still wrong up to some powers of the square root of the fourth root of minus 1 that really depend on the conventions you like for supersymmetry algebras. There's a similar formula for the dependence on the area, which will be the z component of the supersymmetry algebra in the boundary. Now, this component vanishes if the boundary theory is superconformal. And so for the rest of the talk, I'm only going to assume that the boundary theory is superconformal so that I can ignore the area dependent. So I really don't have an area dependent function. So I want to say this is a function, this is a holomorphic anomaly equation. This is saying that the Witten index of y is not a holomorphic modular form. It's a real analytic modular form with a prescribed holomorphic anomaly. And this is basically like a kind of a Moss form. It's a version of a Mach modular. So I'll say that on the next slide, I think, yeah. So in addition to being modular net before and now kind of, modular, well, real analytic modular with prescribed holomorphic anomaly now, in the compact case, we said that the Q expansion was integral. Any nice enough real analytic modular form has a Q expansion. The way you do it is you analytically continue, and then you take the limit as tau bar goes to minus infinity. This limit just completely breaks modularity. It really breaks it, unless you were already holomorphic. And then but you can still talk about the Q expansion of this no longer modular, but now holomorphic function f. And this function f is what is basically what's called a generalized Mach modular form. Generalized Mach modular forms are the same pretty much as analytically nice real analytic modular forms. You can go back and forth between the functions I'm calling f and f hat. And so anyway, this Q expansion in this case, you can still recognize as a supersymmetric index, and so it's still integral. Actually, there's a footnote that I'm not going to emphasize, which is that there's some x-dependent shift to integrality that has to do with the Theo-Johnson-Freyd invariance. So our conclusion is that when y is an SQFT with cylindrical ends x, and when x is superconformal, then this limit is basically an integral generalized Mach modular form. And the holomorphic anomaly is called in the Mach modular forms literature called the shadow of that Mach modular form. And again, we checked this carefully in some sort of non-trivial examples. So contrapositively, if you only know x, then you know the shadow of the Mach modular form. So if you only know x, you could ask, can x be filled? And filling x would be the same as producing a null homotype b of x, because if you had a null homotype, you could compile it into a filling. So if you only know x, you can compute the shadow, you can compute the shift of integrality, and then you can ask, does there exist an integral Mach modular form with that shadow? And the answer is usually not. If you just write down some random function g, which you want to be the shadow of a Mach modular form, well, it's always the shadow of a Mach modular form of a generalized Mach modular form with complex Q expansion, with C Q expansion, but it's often not the shadow of something with integral Q expansion. And there's an explicit obstruction to it being in the shadow, and it lives in this specific group. The group is the quotient of complex valued Q series modulo Z valued Q series plus complex valued holomorphic modular forms. And our theorem in quotes, because we didn't check some details, but we gave, I think, a good argument. Okay, so our claim, if I were giving a math talk, I'd call it our conjecture, is that that this obstruction really is a deformation of the boundary theory X. We call it the secondary elliptic genus or the secondary Witten index. I'm going to use those words interchangeably because it came from applying. So in general, in topology, there's not a precise notion of what secondary invariants are in topology, but usually you call something a secondary invariant when it comes from pretending that you had a filling and applying your primary invariant to the filling, to the null homotopy. So let me go back to the motivating examples. So remember that at least in the far IR, I cared about the round 3 sphere with string structure of strength K, and in the far IR that was a WZW model with WZW level K. The supercurrent has a standard form. It's basically a trilinear in the fermions with a specific proportionality factor, and then something proportional to boson-fermion combination. The boson-fermion combination will never be able to soak up all 3 of the fermion zero modes, and so it won't have a one-point function. And so the one-point function of the supercurrent is just, well, there's a proportionality factor. Then each of the fermions gives you a factor of the Dedekind zeta function of tau bar, because they're right-moving fermions. And then there's the residual, the bosonic part of the WZW model, which just contributes the partition function of the WZW model. And this is supposed to be the shadow of an integral Mach modular form. And very conveniently, Harvey, Murthy, and Nazaroglu, for other reasons, had already written down an explicit Mach modular form with this shadow. And so if you take their explicit Mach modular form and compute with it for a while, you can figure out what class it is in my group. So you can figure out the obstruction to this theory having a null homotopy. And that class is K on 24. The factor, the denominator 24 really comes from this it really comes from the Z2 part. So so the conclusion here is that since this is K on 24 modulo integers and modular forms, and so the conclusion is that S3 is not null homotopic when you're not at string structure divided by 24. And so that was our result. So for the last, I guess I get 10 minutes left. Let me say just a few things about why we did this and what my mathematical motivations were. So what was going on for us thinking about it is that there's a large open conjecture mathematically, which has one version of it, I think, has been due to Stoltz and Teichner, but they were building on work of Witten, Siegel, and Hopkins, and others. And the conjecture is the following. The Witten index, the primary Witten index, that was a map from, the way I set it up was a map from supersymmetric quantum field theories in minimal 0,1 super SPFTs to integral modular forms. And the conjecture is that this index has a topological refinement that I'm going to call the topological Witten index. which lands not in modular forms, but in a topological enhancement of modular forms called very creatively topological modular forms. Topological modular forms, so modular forms are a ring. Topological modular forms are not a ring. They're a much more homotopic object. They're what's called a ring spectrum, or equivalently a generalized cohomology theory. And so that's the first part of the conjecture, is that there is such an enhancement. TMF is a well-defined mathematical object. The second part of the conjecture, which is the part that's I think most exciting, is that actually this topological Witten index should be a complete invariant if you topologize SQFTs correctly, like for the sort of this natural topology that I was telling you about at the beginning. Meaning that the space of SQFTs, so I should say the space of SQFTs is naturally a spectrum. It's not just a topological space. And the conjecture is that the space of SQFTs, it's naturally a spectrum. The conjecture is it's equivalent to this spectrum from mathematics called topological modular forms. So I'll sort of too quickly tell you the rough mathematical definition of topological modular forms. I want to emphasize topological modular forms exists mathematically. Its only description right now in mathematics is totally algebraic and uses some pretty hard derived algebra. So one of the reasons why a topologist would be really excited, why I'm really excited about this conjecture, is because it offers an analytic model of this object topological modular forms. And there's a very analogous story with K-theory where having analytic models of K-theory, especially ones that come from physics, is very useful for doing mathematics. But currently the only definition in mathematics, I'll tell you a sort of bird's eye view of the definition. So modular forms, their definition is that you take the stack of elliptic curves. This stack has a graded vector bundle that I'm just going to call V, whose graded components are powers of the Lie algebra of the elliptic curve. This vector bundle, its fibers are the coefficients of a cohomology theory called E-elliptic cohomology. And then Gorse, Hopkins, Miller, and Lurie worked really hard to produce, to enhance this from, rather than just being a stack of vector bundles, to really get a stack of cohomology theories whose fibers really were re-elliptic cohomology. And they had to basically invent derived stacks and derived elliptic curves to do this. But at the end of a lot of hard work, then we do have a derived stack of elliptic curves, a bundle of spectra on it whose fibers are elliptic cohomology, and by definition, topological modular forms is the global sections of that bundle of cohomology theories of spectra. And so that's the algebraic definition. It's like, the problem is that this, I emphasize it's algebraic because we don't have any, like, modular forms have analytic models. They're like the moduli stack of elliptic curves is an analytic object. It's kind of complex tori, if you want. Whereas derived elliptic curves really don't. They really only exist in algebraic geometry. So that was the big conjecture that led us to this. And the map from TMF to modular forms is quite well computed. It's quite well understood in topology. And so if you believe this conjecture, then you would say that the map from SQFTs to modular forms is also quite well understood. And what we know is that it's not an isomorphism. It is an isomorphism after tensoring with a complex number. So that means that the only thing that it fails to be an isomorphism on is torsion stuff, is elements who, when you add them to themselves enough times, you get to 0. And Bunke and Naumann had already written down, using algebraic topology, they'd written down what they called the secondary Witten genus for TMF classes. And they computed it for S3 with string structure K and showed it was non-zero except for when K was divisible by 24. And that's why, and then what we were doing with Davide was to try to understand their invariant using physics constructions. Their invariant made no explicit reference to Mach modularity. And I think, but I'm pretty sure that we wrote down a version of their invariant. I'm working with Dan Berwick-Evans to give a proof of that. That's a kind of mathematical proof. or rather, we're going to try to write down Bunke-Naumann's invariant in a way that makes explicit reference to Mach modularity. And I want to mention that the secondary invariant still misses some of the torsion in TMF. There's still things in TMF that are not seen, that we don't know how to see very well in topology. And so similarly, that means I don't have any clue how to see them in physics. So I have an invitation to all the physicists, which is the group manifolds. If you take a group manifold SU3, spin 5, or G2, and take the corresponding sigma model for that group manifold. So again, this will flow to some WZW model. And I want basically the level 1 theory. So this is where you use the string structure that comes from the left invariant framing. So those classes in TMF are known to be non-zero, but proving that's hard. So the question is, to find an invariant of quantum field theories to show that the corresponding sigma models are not null homotopic. So anyway, I'll just end by saying something too brief and too vague, which is another reason why I was really thinking about this stuff, and where I'd love people to give me ideas. As I said, these null homotopies of interest in quantum field theories, that actually gives you a source for integral Mach modular forms. And you could, of course, do this all with a flavor symmetry, and then you get Mach modular forms that are valued in characters of G. And we have 30 years of experience knowing that 2D quantum field theory is good for explaining modularity in moonshine, including the original monstrous moonshine. And in the last decade or so, there's been a lot of interest in Mach modular moonshines and umbral moonshines. So my hope is that this might help explain the Mach modularity in umbral moonshines. There's a little bit more to being moonshine that's not just modularity. When you say something's moonshine, it's easy to write down modular functions, modular forms. To say something's moonshine, you have to have a genus 0 or optimal growth type condition. So some very strict control over the behavior of the functions of the cusps. And in the case of umbral moonshine, I think the best way to say this would be to work with what you might call topological cusp forms. Topological cusp forms are an object that does exist in topology, and I don't know any physics that would explain it. And so this will be the end of my talk. I just want to put an open question, which is first of all, what physics gives strongly holomorphic modular forms? The Witten index a priori is a weakly holomorphic modular form. It's allowed to blow up at q equals 0 with a pole. And even more importantly, what physics gives what gives cusp forms, gives functions that vanish at q equals 0. If we could come up with some natural space of field theories where the partition, the Witten index were always cusp, that would really, I think, help to explain things like topological cusp forms. So thank you for your attention.
Let's thank Theo. Edward, you have a question?
The title suggests that my question might be answered by the last paper on your last slide. My question was, what are the manifolds? My question is, what are the manifolds with boundary that are supposed to be relevant to umbral moonshine?
This is a deep question, and let me say that I don't. The answer is, so let me say that what I've kind of have a proposal for is only the A1 version of umbral moonshine, only the original Metsu moonshine. And it's just a proposal. I don't have, there's some aspects of it I don't know. In the first paper I mentioned on this slide, on the holomorphic SCFTs paper with Davide, we kind kind of studied some interesting theories where we certainly, all right, I should just say this as a general thing. There are plenty of field theories where you don't know any sigma model description of the field theory. And it's, if you believe that SQFTs are the same as TMF classes, then it's a hard theorem of Mike-Hopkins. Well, there's a theorem of Mike-Hopkins that says every TMF class can be represented by a manifold, not canonically, but I don't know how to reproduce any argument like that. His proof is like by just computing things. And so what I think for Umbral-Moonshine, the naive guess for Umbral-Moonshine, which I think is wrong, and which I argue is wrong in my recent paper, is that you should be kind of really studying punctured K3s. And I'm pretty sure that by itself ain't good enough.
What's the naive argument for that anyway?
So as sort of we talked about in our paper with Davide, if you take a K3 and puncture it 24 times,
yes,
you can put a string structure 1 around each of those punctures.
mm-hmm.
And if you flow those punctures to the WZW, those spheres to the WZW limit, what you do just get the Mach modular form. That K3 surface, punctured K3 surface itself, just does produce the Mach modular form from Matsu-Moonshine, because it's a version of the elliptic genus of the K3 surface. So that was great. Now this is supposed to have something to do with M24. And the natural thing then to do would be to try to permute those 24 spheres, those 24 punctures. You certainly couldn't do that permutation at the level of manifolds, but maybe you can do it with kind of more quantum theory objects. And then if you actually try to do that, you find out that when you actually try to do that, then it doesn't work. Like you don't get the right Mach modularity that's predicted in Umbral-Moonshine. What I actually think the right answer is that, so I don't know what the bulk theory, what the sort of filling theories should be. What I have is a guess for what the boundary theory that should be fillable would be.
Yes.
And rather than being related to kind of 24 copies of an S3, I think it should be related to John Duncan's super moonshine theory, VF natural. VF natural is a unifying object for all of the Metsu groups, all of the Umbral-Moonshine groups, because it has a Conway symmetry. And you could try to see if like some version of it is null homotopic. And that's my proposal in the paper. This gets into the difference between, so maybe I'm saying things that are too vague, but if you're not doing topological objects, there's no real difference between cusp forms and strongly holomorphic modular forms. The spaces of cusp forms and strongly holomorphic modular forms are isomorphic by multiplying by Dedekind's delta, by delta. There is no topological modular form delta. The smallest topological modular form is like, instead of delta, there's 24 delta. And one of the costs of this is that topological cusp forms are just different from topological strongly holomorphic modular forms. They're just different spaces. And so you can really tell the difference between sort of different, like there's just very different conjectures about whether you're working with cusp forms or, I'm not saying things that are clear. Sorry.
Okay, thank you.
Greg Moore has a question. Please unmute yourself.
Hi, Theo.
Hi,
So
Greg.
I wanted to make sure I understood properly. Your Mach modular forms are not quite the same as the Mach modular forms as in the definition of Svegers. Is that correct?
Well, there's sort of, I think the main thing to say is that so there are at least 3 things that So the most strict version of mock modular form, like if you look it up in kind of, I think Sveigers and certainly Wikipedia would tell you that the shadow function should be maybe anti-holomorphic, or the holomorphic anomaly itself should be anti-holomorphic, so that you get some equivalence between mock modular forms and harmonic Moss forms.
Exactly, yeah, that's where I was going. I was wondering if you had some analog of the iceberg.
Right, and so then there's sort of an intermediate thing which are called mixed mock modular forms, where the shadow is the dot product of a vector valued modular form with a vector valued, like with the complex conjugate of a vector valued modular form. So it's a finite sum of things like that.
Okay, sure.
And then the most general thing is just generalized mock modular forms where the shadow could be any real analytic function.
Okay, so the shadow could be a Moss form or something like that.
Right. So a priori, our invariant uses arbitrary real analytic modular functions.
I see.
But this is just a question about the boundary theory. It's just a question about the theory I was calling X, and not a question about the filling Y. And so if X itself happens to be, remember, my invariant really isn't, like, I need to do more to tell you my invariant when X wasn't super conformal anyway. So when X is rational, then you're in the mixed mock modular case. And when X is anti-holomorphic, then you're in the pure mock modular case.
Right.
And so, for instance, in my Matthew Moonshine paper, I propose a specific X which is anti-holomorphic. And so really would give the specific, like, at least it has the right, you know, at least it does produce pure mock modular forms for that example. And in the case that I told you on the slide, it was about mixed modular forms because the shadow was rational.
Okay, I had another question.
Go ahead.
I know you've explained this to me before, but it would be useful for me to hear it again, and maybe other people too. Could you explain why the space of supersymmetric quantum field theories, 0-1 theories, is a loop spectrum? I think you said it's a spectrum. It's a loop spectrum?
Yeah, it's sorry, my iPad went asleep, so I'm surprised that it's still displaying. So I should first say that every author seems to have a different definition of, like, use the word spectrum slightly different. There's all these different models of spectrum. So we claim it's a spectrum in the way that, in the sense that NLab uses for spectrum, and that Wikipedia calls an omega spectrum, and maybe you're calling a loop spectrum, which is that the loop space of one piece. So what is a spectrum? A spectrum is a sequence of spaces, and then there should be some relation between each space and either the loops of the next space or the suspension of the previous space.
Exactly, yeah.
And the difference between different models is exactly how strict you want that relation to be. And I think a loop spectrum is one where each space is homotopy equivalent to the loops of the next space.
Okay.
So the spaces here are spaces of field theories with prescribed gravitational anomaly. The gravitational anomaly in 2D takes integer value or half integer values, and I can prescribe the anomaly, and that gives me my sequence of spaces. And then in one direction, so what would a loop be? Well, it would be a family of theories that starts at a null theory, walks around, and then comes back to a null theory. So if you have such a family, you could try so that had some parameter along the loop. You could try to dynamicalize that parameter. And okay, there's some analysis that would need to be done, but our claim is that the results of that dynamicalization process, because you started and ended at kind of with spontaneous supersymmetry breaking, the result of that would be again compact, because it's like basically it's like the integral of a compactly supported function. In the other direction, it's really easy. If you have a theory, you can do my Lagrange multiplier trick with the function 0. So, which is to say, you can take your theory, put on turn on a fermion to be the Lagrange multiplier, turn on a superpotential, which is just epsilon times lambda, And now you got a family of theories where you just, and except for when epsilon is 0, that family has supersymmetry spontaneously broken. And so I had a family that like lived at null, jumped through my theory, and then go back to null. And then you have to convince yourself that these two maps are homotopy equivalent.
Exactly. Yeah, right. That was, yeah, indeed. So I mean, is it easy to see that's a homotopy equivalence?
One of the two compositions is easy. If you start with a theory, turn on, like do this stupid thing to get a family and then integrate back out, that obviously gets you back to your original theory. Up to some, I mean, it doesn't have to be the original theory in the notes. It has to be deformation equivalent to the original theory. So that composition is easy. The other composition is, would require that I be more careful with a lot of analytical issues about what I mean by families of theories. And I own, like, one question you could ask is if you have, like, maybe you have a family of theories. First of all, I don't really want to even imagine that my theories always have, like, Lagrangian field theoretic descriptions, but maybe they do. And then you could ask, like, as you move along the family, are at least the field content the same all the time? Or maybe the field content itself is allowed to jump? But probably you could always make the field content be the same all the time just by, like, if you have some fields for some along the family, that for some piece of the family, just extend it to the rest of the family, but make it very massive. And if you can do something like that, then I think there's an argument that can be done.
Okay, thank you.
Hank Chen, please unmute yourself and ask your question.
Okay, hello.
Hello.
Okay, so thank you, Theo, for the very interesting talk. I'm not like, there's this proposal, right, by Douglas and his co-author, where he tries to propose a geometric realization of TMFs in terms of bundles of boundary conditions.
This is Douglas and Enriquez, I think.
Yes,
Is that what you're thinking of? Yes, I know that paper quite well.
Right, okay. So I guess there's a connection between what you're proposing as the analytic model for TMFs and their proposal.
That's exactly, well, I don't, so one of the things that I'm aware of that Andre and Chris, I'm only really aware of one paper of Andre's and Chris's about proposing models of TMF, and it's their one about superconformal nets. Mm-hmm. And what I sort of think that they're doing is they have the same conjecture I have, that TMF should have an analytic model as some version of quantum field theory, of the space of supersymmetric quantum field theories. And now there's like a math question, which is to write down mathematical definition of quantum field theory. And I think that definitions in terms of nets of von Neumann algebras like they use are probably not the final definition, but very close to giving a mathematical definition of quantum field theory. I think that, that Andre in particular has some really good ideas of what, I mean, I've talked to Andre more than I've talked to Chris, but I think they're, so one of the issues is that in the papers that they look at, they're only looking at like they look at sort of defining conformal field theory or superconformal field theory rather than quantum field theory.
Right.
And this is reasonable at a, like, for what we can do. Kind of, I think we're close to having a complete definition of conformal field theory in 1+1D, and quantum field theory is still a ways off. But it's important, if you actually tried to make, like, you could have conjectured TMF would be modeled by superconformal field theories, by some space of superconformal field theories. And this conjecture is kind of definitely false. The space of conformal field theories is probably, like, if you're in the space of conformal field theories, you roughly, at least if sort of generically, you think that maybe there's only finitely many directions that you can move around the space of conformal field theories. And on the other hand, you could have tried, well, now there's a question that I don't know the answer to. So you could imagine starting at any quantum field theory and flowing down to the far IR and hoping to hit a conformal. And so you could try, and this is like a, Zamenhof-C theorem tells you that that's roughly a Morse flow down to some kind of critical locus.
Right.
And so you could try to use the conformal field theories as a way of understanding through kind of Morse theory, a way of understanding the space of all quantum field theories. But then you have to just understand what the kind of flows, kind of what the RG flows from a UV CFT to an IR CFT are. And you'd have to kind of work that into the topology. So this sounds great. I would love for that to work. I see no reason why it doesn't, except that I also see no reason for the IR, it's important that you always stay in compact theories. And I think the experts seem to believe that if you started a compact theory, the far IR might decompactify.
Right. And that's where the analyticity becomes important.
And so that would bother me. I mean, in particular, so every expert, like every time I visit somebody, every time I get to talk one-on-one with sort of an expert, I try to get them to answer this question for me. And the naive guess is always, yes, it can decompactify. In fact, the naive guess is always you just start with a surface of high genus and write down the sigma model, and of course it's going to decompactify. And when you try to run that argument really carefully, well, that wasn't UV complete until you UV complete it, and maybe something funny happens when you UV complete it. But these are questions I don't know the answer to.
Okay. Well, it's interesting how like the actual analyticity will affect the topology at the end.
Yes, but also somehow you should expect it. So a lot of there's a baby version of this conjecture, which is a theorem about K-theory, which says that K-theory has a model in terms of the space of minimally supersymmetric quantum mechanics models.
Is it are you talking about operator K-theory? Or?
Sure. That's, I mean, what you might call topological K-theory. Right? Now my computer realized that my iPad was asleep, so I'm going to turn it off. So topological K-theory, either KU or KO, can be modeled in terms of the space of quantum mechanics models. There are multiple models like that. What's a quantum mechanics model? It's for this version, it should be basically some type of Hilbert space with some type of Hamiltonian. And there's all sorts of analytic questions you have to ask about the Hamiltonian. Hamiltonians are almost always unbounded. So this is a theorem. When you say the right adjectives, when you say the right analytic adjectives, there are multiple choices for those adjectives, but not all choices work. And you do have to set the adjectives correctly.
Okay.
I'm going to try to fit in another question or two before the top of the hour. I remind everybody to please email Jeff if you want to go into either the session 1 room or the session 2 room at the top of the hour. But I'll keep moderating questions here in this room for Theo as long as that's possible. And let's have a question from Sharyar. Please unmute yourself and ask your question.
Thank you. And a statement about the session for letting Jeff Morgan know, do we have to email him or just do it in the chat?
I think in chat.
Okay,
in chat,
that's
yeah.
good. So the question is about, well, thanks, a very nice talk. The question is about TMFs. In the classical case, there is an action of Hecke operators on cusp forms, and the cusp forms which are Hecke eigen, those are very special because there's L functions associated with them and motives associated with them. And a Hecke operator can actually be thought of very geometrically as a correspondence on the modular stack, as you said. So because of this definition as a correspondence, it seems that one can get an action of Hecke operators on these topological modular forms as well as a factor of some derived categories. So is it known? And are the TMFs which are Hecke eigen, if that makes sense, are they more special than the other ones?
So parts are known and parts are, I think, haven't even been considered yet, to my knowledge. So let me try to say what I'm aware of. So now, maybe 13 years ago, Nora Ganter explained that, and also well, certainly Nora's papers are some of the best ones. So she was looking at Devoto elliptic homology. So that's basically equivariant elliptic homology for finite groups with but complexified. So not seeing the integral structure. Mm-hmm. And she explained that Hecke operators there are extremely closely related to basically are kind of power operators, or basically Adams operators for TMF. And
so let me ask.
She was sort of interested in that for like what she was interested in was questions about moonshine and about kind of replicability in moonshine. The integral stuff, I think a little bit has been done for Hecke operators on weakly holomorphic TMF classes. Topological cusp forms, I'm only aware of one paper where they've even been mentioned. Most of what I know about them comes from kind of reading unpublished papers and drafts by various experts in algebraic topology. So I just think that the topologists simply have not explored cusp forms.
I see, thanks. So the analog of Hecke operators, do they satisfy, so Hecke operators satisfy the property that Hecke operator for, well, first of all, Hecke operators are parameterized by integers. And if you take the composition of Hecke operator for n times a Hecke operator for m, it's equal to Hecke operator for n times m. I mean, they're multiplicative, right. That's the word. So these atom operations also satisfy this multiplicative property?
You'd have to look into the literature. This is not my expertise. I also see in the chat that David says they're related to permutation orbifolds of powers of the theory. And this is exactly where Nora's paper starts. That's why she was interested in it.
Okay. I think Adams operations are multiplicative, but I don't completely remember. But let's move on to Pavel. If you have a question, please unmute yourself.
Hello. Do you think it could be possible in principle to construct, like in a similar way, some sort of tertiary invariants, which would be kind of secondary invariants to invariants that you construct, and would maybe capture some sort of torsion in TMF in degrees 2 modular form, not 3 modular form, but 2 modular.
I would love for that to work, to write down tertiary invariants. I failed when I tried.
But it was some sort of technical problem or more conceptual?
Go ahead, Theo, analyze your failure in detail.
Yeah, so, I mean, it's always hard to tell when you fail if it's just like your own personal sort of inability. So the problem is that to write down, so the secondary invariant of Buchan-Naumann has a beautiful description due to Dan Berwick-Evans in terms of what Dan calls KMF, or kind of K-theoretic modular forms. And what you discover from that description is that what's going on really is an interplay between kind of the two properties that you know about the Witten index, namely that it's modular and that it's integral. And either one of those doesn't give you an obstruction, doesn't like give you an interesting secondary invariant. Just, but when you play them off each other, you get a rich secondary invariant. If you knew a third property, it would be easy to write down a tertiary invariant by playing that off of it too. Another way of asking this question is our invariant, the way we described it, had to do with the one-point function of the supersymmetry operator. If you could tell me anything about that one-point function beyond that it was a real analytic modular form of some specific weight, if you could tell me anything more about it, if you could tell me some interesting integrality or some interesting anything, then we could try to play off of it. But all I know about it is its weight as a modular form.
Thank you.
Okay, we have a question from Mykola Dadashenko. Please unmute yourself and ask your question.
Hi. My question is a little bit tangential to the main topic of your talk, but since you mentioned how to make sense of this cigar-like non-compactness, I wonder if there are any other types of non-compactness you know how to deal with, specifically conical, for example.
I don't. So is that really true? One of the things that I mean, the short answer is no, I don't know how to make sense of things because I haven't thought them through carefully, or I haven't even tried. The slightly less short answer is sometimes there's procedures that allow you to trade different types of non-compactness for each other. So there are ways so in the cigar case, one of the ways to construct the cigar is to start with just a flat plane, two-dimensional plane, the complex line, and then do some procedure to it that converts it into a cigar, where you kind of do some Kähler reduction for the U1 action. And I could imagine similar procedures to trade different other types of non-compactness. I don't know.
Okay, all right, thanks.
Okay, let's thank Theo one more time. Sorry, you can unmute and join me in thanking him. And we now have breakout session. If you have not been assigned to one or whatever, you still want to express your preference, you can send Jeff Mergen a chat and he'll put you in the correct room. Otherwise, I think you stay in the main room.
Great. Thanks, Dave.